Hello everyone, my name is Bludau, and in the next 15 minutes I will present our work regarding feature sets in just-in-time defect prediction. First of all, let me just quickly introduce defect prediction. Defect prediction automatically identifies defective classes or modules in a new software release in order to reduce testing and reviewing efforts and find defects before they occur in a production environment. In just-in-time defect prediction, these methods are applied on every new commit to the system, which has several benefits. First, the prediction is available early after the initial development task is accomplished, which leads to faster reviews. And second, predictions on a change level contain a smaller amount of code, leading to more targeted reviews. In the last years, deep learning approaches are more and more often applied when trying to enhance the performance of just-in-time defect prediction approaches. However, they are shown to not necessarily outperform more traditional metric-based approaches, and therefore researchers have suggested to investigate current and also additional features that could be used with defect prediction. In this study, therefore, we compare different just-in-time defect prediction approaches with state-of-the-art features and also investigate two novel feature sets, assessing their effectiveness and discuss their expressiveness in different project setups. So let me now introduce you to the different features that are used for just-in-time defect prediction. Many studies have already evaluated the effectiveness of just-in-time defect prediction on different open source or industrial projects. And there a variety of features from different aspects of the software development process were already used and proposed in existing literature. And a combination of these features is often used together as a baseline for new defect prediction research. And this is shown here on the right. I will not go into detail of all these features because they are well known and well studied, but just let me say that there are different aspects and different dimensions to these features that shed light on different aspects of software development. For example, there is the size of the change, but also the experience of the developer. So many aspects of development activities are already investigated and contained in the state-of-the-art features. However, we think that current software development practices do not develop tasks in only one commit, but rather have multiple commits representing one feature. And therefore, we propose additional workflow-related features. So if you look at the slide on the left, we have depicted a schematic feature development where you have a version control system on the top and a pull request on the bottom of the image. And as you can see, one pull request, one feature development can contain different commits on a separate branch, for example, and have comments and discussion about the feature development. And only once the feature development is done, it gets merged back to the main branch of the version control system. The intuition here is that the development activities inside a feature they contain information about the defectiveness of a feature, and also that over time in this feature development, the riskiness of a new commit introducing a defect changes. And therefore, we propose the features here on the right containing feature development features over time. So for example, we have a size dimension here where we first report the time already passed in the feature development until the current commit, and also the position of the change within the features. Then we accumulate the number of added lines in the feature over the feature commits and also the lines deleted, and also report the share of current changes compared to the whole feature development. For the diffusion dimension, we use the same calculation as before, but accumulate over all the past commits in the feature. And then we have some proposed some continuity features which show the number of commits since the last release and also since the last developer change. And we report also comments on the pull requests, so discussions or additions. Another thing that is not often looked at in just-in-time defect prediction is the structure of the change. And therefore, we illustrated on the left of the slide the changes of a function in the abstract syntax tree. So if you look at this image, you can see version 1 of a function on the left and version 2 of a function on the right. And different things can happen during a change. For example, as you can see here, we have added a parameter in the function, we have removed the else statement, or we have updated one condition in the if clause. And these features are not often represented in just-in-time defect prediction. And so we propose some different features concerning the changes in the abstract syntax tree of a commit. So first of all, when we look at function level, we report the number of functions in all files that were changed. We also report the size of these changes and the difference of the size in the changes. Also, we report the number of added, removed, or changed functions. Then we have some features concerning really the changes in the nodes of the abstract syntax trees. And there we look at added, removed, or updated nodes, and we cluster these nodes also in their usage. So for example, we have some special nodes like for loops, if statements, or we have some comment nodes. So if a comment was added or removed in a change. And also we cluster primitive changes to tell if numbers or strings changed. And last but not least, we report on the depth of the change. So we take the abstract syntax tree and look at how deep were nodes changed. And this should represent how difficult it is to understand the change. Before we come to the results of our study, I just wanted to show you the study design real quick. So first of all, we have a data set containing 6 open source repositories and all information about defect introducing commits that was recently published. We then did download the data from GitHub and Git for these repositories and extract all the features according to existing literature, or as I just described in the last 2 slides. We then did some data processing, neglected outliers, and also because of the imbalanced nature of the data sets, did apply random downsampling. We then used these features and the labels in the data set to learn just-in-time defect prediction models. We learned different models, also did learn effort-aware models. However, because of time constraints, I will not go into detail on effort awareness in this talk. We then evaluated all the results in 3 different scenarios. First, we did a 10 times 10-fold cross-validation, and then we did also 2 more timely evaluations. First, a short-term validation where we only use the last 2 months of development to predict the next 6 months, and long-term validation where we use the complete project history up to 1 point and then evaluate on the next 6 months. And for the evaluation, as I already said, we did do standard performance metrics like precision, recall, F1 score, and Matthews correlation coefficient, but also did effort-aware metrics, which I will neglect in this talk. However, the evaluation for the effort-aware metrics is quite similar to the other performance metrics. So let us take a look at the results of our study and first the overall predictive performance of the models trained with the different feature sets. In this table, we have the model results for the 6 investigated projects trained with the different feature sets as rows, and in the columns we see the 3 different validation settings. For a first overview, let us take a look at the values for the Matthews correlation coefficient in a cross-validation setting. We see that the different performance results vary from project to project and with the used feature set. In Angular, for example, the state-of-the-art features provide the highest MCC score. In Jenkins, the best performing features are the workflow features. In Kafka, the features have the highest performance score related to the abstract syntax tree extraction. And in the Airflow project, no single feature set can clearly outperform any of the others. However, the combination of all the feature sets does increase the MCC by 8 percentage points in this project and provides the highest score for every other project as well. And also, this is true for the other two evaluation settings. Interestingly, the performance improvement with respect to each performance measure is higher in the time-dependent validation, so short or long-term validation, than it is when cross-validating the results. This may indicate that the predictive power of the different feature sets shifts over the life of a project, and that no feature set therefore performs best over the entire project lifecycle. And when we look at the effort-aware metrics, a very similar picture emerges. We investigated also whether the differences in performance between state-of-the-art features and the other feature sets are statistically significant. Therefore, we use the Wilcoxon-signed rank test, and we compare the feature sets against the state-of-the-art validation. And here in the picture on the right, you can see this for the cross-validation. Additionally, we employed a Cliffs delta to measure the effect size of the difference between the feature sets. As I said on the right here, you can see it for the cross-validation and the MCC. And you can see that the models using all features increase the performance in terms of MCC significantly in all the projects with a large effect size and on average with an increase of 21%. The workflow features do only increase the MCC for the Jenkins project with a small effect size, and the path features improve the model performance in 3 out of 6 investigated projects significantly with a medium to large effect size. We evaluated this for all the metrics and validation settings of our study, and we see that the combination of features does have a significant effect on the performance for every other performance metric in a very similar way. Therefore, we can conclude that a combination of feature sets and sources can improve model effectiveness over the improvements that one single additional feature set does provide. Last but not least, we execute the non-parametric Scott-Knott-ESD test to see which features are most important. We use the feature importance of the random forest models in the cross-validation for that. And the table on the right shows the results of this analysis with the top 3 most important features per project. We can see that the path variables have an important influence on the model performance in general. The added nodes to the abstract syntax tree and the depth of these nodes are the most important features. Also, we can see that there are project-dependent differences. For example, the cumulative lines that were added in a commit are most important for the Airflow or Angular project, but are not really important for the Calcite or Kafka project. Also, we found that some features are not deemed important in any of the projects. For example, the number of comments on a pull request. And we can now conclude that all the different feature sets contribute to some extent to the overall predictive performance and are really dependent on the project setup. So to conclude, the novel feature sets can improve the performance of just-in-time defect prediction models and do outperform state-of-the-art approaches. The models are showing varying performance dependent on the used features, and the combination of features improves the prediction results in all cases. We see that the new features especially evaluate effort-aware metrics. Especially the abstract syntax tree change features, for example, the number of added nodes in the abstract syntax tree, have a high importance on identifying defective commits for all investigated projects. Last we see that the features and the used data sources to collect the features should be selected with care to include the most differentiating features in all settings. Thank you very much for your attention, and if you have any questions regarding the topic, please feel free to contact me.